Welcome back, ladies and gentlemen. In this video, I would like to do some quick review to see that the ideas from the previous video regarding simple harmonic motion apply to sort of universally, not just to a mass on a spring. So we'll look at that, and then we'll get into this idea of how energy is conserved with simple harmonic motion. So here we go. With any simple harmonic motion, you can find the position of an object with respect to time. So you have the amplitude times the cosine of angular frequency times time. And you have a way to find the velocity of an object where you have the opposite of amplitude times angular frequency times the sine of angular frequency times time. And you have a way to find acceleration of an object. And in this case, what you're looking at is you still need that minus sign. And you have amplitude there, and then you have the angular frequency squared, and you are dealing with cosine of angular frequency times time. So those are sort of like three important equations of kinematics, so to speak, for an oscillating system that's displaying simple harmonic motion here. There's a couple other relationships as well. This idea of angular frequency, as far as a mass on a spring goes, this is specific to a mass on a spring. This one right here, you have this relationship, and so from that, we developed an equation for the period of a mass on a spring, and it comes out to be 2 pi radical m over k. Okay, so the first three equations are sort of universal to all simple harmonic motion, and then these two are specific for a mass on a spring. Kind of title overrunning my equation. Sorry about that. Now, the point I want to make, though, in the quick review here is that these guys apply also to a pendulum within certain limits. And there are similar equations, or I should say a similar equation for the period of a pendulum, a mass oscillating back and forth as it swings on a pendulum. So we're going to get into that, and we'll have to use these relationships here and make this work for us. So let's take a look at that. From an idea of conservation of energy, though, first we'll take a look at how this is working for a mass on a spring. It's something that should be pretty familiar. You guys recall that when energy is conserved, you have the sum of kinetic plus potential. Now, with a mass on a spring, kinetic energy is, it's a mass and it has a velocity. So there you go. But now the potential energy of a spring is 1/2 k x squared, right? Okay, fair enough. And that gives us the total energy. But this location, the position of the mass as it oscillates back and forth or up and down on the spring, right? That position has a maximum value, and you could find this position from the equation we just saw. So amplitude times cosine of angular frequency times time. So we'll do a quick substitution here into this. Let's just look at the potential energy for a second. We're going to make that substitution. We'll say 1/2 k times this business for x. All right. So a cosine omega t, and that is squared. Don't forget the exponent. So the potential energy of a mass on a spring, just the potential side, just this little bit, comes out to 1/2 k a squared times cosine squared of angular frequency times time. Okay, fair enough. But check this out. Where would the potential energy be at its greatest value, right? So let's investigate that business, maximum potential energy. Well, essentially, it's going to be where cosine squared of omega t here is equal to 1. And when that's the case, you're at your maximum potential energy, and you can find that value by 1/2 k a squared. It simplifies quite nicely. Cool. So what about the kinetic energy side now, right? And we can say, well, we know that kinetic energy is 1/2 mv squared, but we have an equation for velocity. Negative amplitude times omega times sine of omega t. So we'll do a substitution here into that part of this equation. M, and we have our a omega sine of omega times time. Okay, but I have to remember those exponents, right? Never lose track of those. Okay, well that should simplify a little bit, right? So we have 1/2 m, and the minus sign goes away once we square it, so this is a squared, this is omega squared, and we have sine squared of omega t. There. Okay, and where will this kinetic energy be maximized? To ask ourselves that. Where will that occur? Well, that's going to occur where you see this business equal to 1. And so the maximum kinetic energy is going to, if you want it to, it's going to simplify out a little bit. But essentially, if you think about conservation of energy, as the energy is transformed from kinetic to potential, your maximum kinetic energy should also be equivalent to this value here, right? So there's an interesting relationship. Well, we see a k here, but here we would see this omega squared and an m. Well, if you recall that relationship, we have a relationship between omega and k and m right here. It turns out that those are equivalent. So we have k max, maximum kinetic energy, 1/2 m, amplitude squared, angular frequency squared. And if you were to work through this, you would see that that value and that value turned out to be equivalent. Okay, and that's because of this neat relationship here. Because of, I'll write it this way, omega squared is equal to k over m. That's what makes these two equivalent. All right, well the next step is, let's map this out a little bit and see what happens, right? A little graph here for you this time. At a displacement of, let's call this A for our x value. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Call it negative A. Okay, and we're going to graph potential energy. Well, there's going to be this maximum amount of potential energy, and it's going to be achieved, let's say there, we'll come across, and let's say there, just on our, for the sake of our graph. Oops, I missed that spot. Whoa. Okay, let's put it there instead. That makes a lot more sense. So, negative. Now, what we see, if you recall from chapter 8, I believe it was chapter 8, where we're dealing with springs and the potential energy of a spring. You essentially had this parabolic shape through that point, and it kind of kept going as far as you wanted to go. Depends on how far you stretch or compress the spring. So, got to mirror that shape over here. My parabola drawing skills are not so hot. Go with it. So here's the deal. at maximum amplitude, right here, and here. That's as far as this thing oscillates back and forth. Well, what that does is it sort of defines a maximum amount of potential energy for this mass on the spring. Right there. So that would be U max for the mass on the spring. And there's more to it though. So what we know, you ought to be able to recognize that right here, this also is the maximum total, or not the maximum, but the total amount of mechanical energy that we see in this system. At maximum amplitude, it pauses for just a moment before it turns around. Literally, it turns around and goes the other way. So there's a name for these points that you'll possibly run into. They're called turning points. Okay, so turning points, right? And each one is a turning point. There's this motion as it oscillates one way, it gets slower and slower and stops, and turns around and comes right back. And I'm not showing motion in physical space. I'm just kind of, maybe I should slide this way, right? Because it's just oscillating linearly back and forth. But because of the relationship between, here we go, because the relationship between potential energy and amplitude is a parabolic relationship, and that's why you got this curve here. Awesome. Well, this U max, well, we figured that out to be equal to 1/2 K A squared. And at the turnaround point, there is no kinetic energy, so you can say also that the total mechanical energy is defined by that level of energy right there. A squared, right? Okay, so this comes about in a nice way. Back over here. Keep this guy handy for you. Something like that. Conservation of energy. So you have kinetic plus potential. And we've already seen that the total energy, 1/2 K squared. Well, what about the kinetic then? If the maximum potential is 1/2 Ka squared, then you can clearly see, and it's kind of silly to go through this, but the kinetic energy is 0 where? At x equals A. That part right there is important to include. Kinetic energy is supposed to be an equal sign. So is that. Sorry. Kinetic energy is 0 joules at x equals A. So when it gets out here, it stops. So we've more or less verified that. There is no kinetic energy at that location or at that location. Awesome. Well, there's one more sort of special location, right? Obviously, right there. How much kinetic energy is there? There. Is there. So let's look at that. So we have now back to sort of the original. And 1/2 K squared. But at this location, from this graph, you can clearly see that there is 0 potential energy at the origin, at the origin or equilibrium position. 0 potential energy there, right? So how much kinetic energy does it have there? It has 1/2 K squared kinetic energy, where at x equals 0. That is important to define, to include in your statement about this. So there is an amount of kinetic energy equal to 1/2 Ka squared at the equilibrium position. There is 0 kinetic energy at the maximum amplitude. There is 0 potential energy at the equilibrium position. but there's maximum potential energy at maximum amplitude. All right, so that's kind of a neat way of looking at things. Now, if you're following along, I'd like to get to a pendulum and see what's going on there, right? Just a quick glimpse at a pendulum. Your textbook does a really good job of explaining how a pendulum really works in some detail. And it's not really hard to follow. The job the book does is really, really good. So we're going to have this thing attached to, let's say, a string. And what's going to go on is we have a vertical line for reference, more or less vertical. And this is what I have to do because I'm a lefty. So I'm going to try to get an arc drawn here to show the path that the pendulum is going to take, at the end of the pendulum, called the bob, the pendulum bob. And so that's the idea. Now, there's some interesting stuff we can label, right? A pendulum will have a length L to it. And now check this out. If we drop a perpendicular line, perpendicular to the vertical, got a right angle, then we have an angle here, the angle theta. We can define a couple other things. We can say, you know what? We know this segment, this distance here to that perpendicular line. That's simply L cosine theta. We also then know this short distance here. Put that down here, and that is going to be L minus L cosine theta. And those are some important things to realize. So there's with a pendulum, the just as it's going back and forth, you have a restoring force, and there will be a distance traveled. There will be a position, a velocity, and acceleration, and those are sort of governed or determined by the same three equations. These guys right here, they work for a pendulum as well, absolutely, within one certain constraint, and that constraint is this. It has to do with the angle. That angle, theta, has to be on the smallish side. You want it less than about 22.5 degrees, or if you like radians, less than about 1/8 pi radians. And your book gets into a really good description of why that's the case. But one thing we can look at is a potential energy curve for a pendulum and compare that to the potential energy curve for a spring, a mass on a spring. So think about a pendulum real quick. If we just have a fixed point in the bob, and we typically would measure an angle theta right there. Now what if we kept lifting it up higher and higher? Okay, well it's now going to be like here, theta has increased, and what if we keep going? Well, it's going to be like here, and theta has increased. And what if we take it to the extreme? Let's go like that. There's our vertical, and look at theta. There's theta. Okay. So this is where we're going to start to see differences between a pendulum and a mass on a spring. I've got another graph here that we'll look at. It's a big graph of the potential energy of a pendulum. And the deal is this. I mean, I'm basically taking the pendulum from a displacement as an angle of 0, down here just hanging free at equilibrium, and I open up that angle more and more and more and more and more until I get all the way up to an angle of pi radians, right, or 180 degrees. So that's the deal. I need to look at the potential energy that's going to be stored there. Let's just go there. That's going to be pi radians. Make sure that's 7. 1, 2, 3, 4, 5, 6, 7. Okay. 2, 3, 4, 5, 6, 7. Okay, and this would be negative pi radians, just the angle the other way. Well, this is very much circular stuff happening, and what this is going to trace out is, as you watch, when theta is close to out here, then the vertical position is changing rapidly. But when theta is close to 180 degrees or pi, then the vertical position is changing very little as that angle changes. And you end up with this neat looking and interesting, basically a sine wave, right? At pi, you would have a maximum value of potential energy stored in that pendulum bob, but it increases and it has a shape like a sine wave. And so we're going to see the same thing on this side. We're just going to complete that, come down. Okay. Well, that's not too bad, is it? So what we have here is the potential energy of a pendulum and the thing is, you should recognize instantly, well, that's a sine curve and this is a parabola for the mass on the spring. And a parabolic shape would be something akin to this. And keep going, and it's not perfect, I'm sorry, but again, like this, and then it comes in, and they do have some things in common. But what you can see, this would be the potential energy of the mass on the spring, right? And what I'd like to illustrate to you, the point, is that for small angles, for angles that are close to zero, that parabola and that sine wave, or sine curve, are really, really similar, right? So, well, about 1/2 pi is like here, 1/4 pi, 1/8 of pi. So you can see for those small angles, I'm trying to illustrate that they're just about identical, and the same on the other side as well. Okay, so your job now is some reading. You have an assignment, and you know, I don't want to put it in here. Read about these topics in your textbook. Read carefully, read thoroughly, please. And as we wrap up this unit on simple harmonic motion, one final thought: be thinking about the practical applications of masses on springs and pendulums. Why are they potentially useful? What use could they be put to? How could they help us test things or measure things? So have those questions in your mind as you read about masses on springs and pendulums, okay? As always, thank you for watching. I'll catch you next time.